Okay, so in this video we want to start to move into being able to differentiate by rule. So that is not needing to differentiate by first principles, but being able to rely on a series of rules for the various functions that we work with. So we want to today focus on the rule for differentiating functions of the form y equals x to the power of n. Now I'm sure this will be familiar and some of you will recall this, or a number of you will recall this from last year. But again, what I want to reinforce throughout this topic is that every one of these rules comes from derivative by first principles. So, for example, if we think about y equals x to the power of n, or f of x equals x to the power of n, where n is 1, so we're looking at the function f of x equals x to the power of 1, so that is f of x equals x. If we then work out f of x plus h, so replacing the x with x plus h, it's just equal to x plus h. And if we then do f of x plus h minus f of x, so there's our f of x plus h, there's our f of x. The x's obviously cancel out, we get h over h, which is just 1, and so we're taking the limit as h approaches 0 of 1. There is no h's in that, so it will just always equal 1, regardless of the value of h. And so therefore we've established that when f of x equals x, f dash x equals 1. The second one, when n equals 2, that means f of x is x squared, f of x plus h will be x plus h all squared, which is x squared plus 2xh plus h squared. And then again, taking f of x plus h and subtracting f of x for our derivative by first principles, the x squared terms cancel out. We can divide by h and we just get left with 2x plus h. Taking the limit of that as h approaches 0, h essentially becomes h becomes 0, and therefore we're left with 2x. So again, f of x equals x squared, f dash x equals 2x. And we can continue that. If we have x cubed, f of x plus h is x plus h all cubed, and we can expand that out. Okay, and then we can put f of x plus h minus f of x, which is up there, and the x cubed terms cancel out, and we divide the other terms by h, it's going to become 2, and we get 3x squared plus 3xh plus h squared. Now taking the limit as h approaches 0, this term will disappear, this term will disappear, and we just get left with 3x squared. And the same follows if we look at x to the power of 4, expanding out x to the power of 4, and our x to the power of 4 terms cancel out when we do f of x plus h minus f of x, and we divide each of the other terms by h, leaving just one of those, leaving 2 of those, and leaving 3 of those, and we get 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Taking the limit as h approaches 0, this term will become 0, this term will become 0, this term will become 0, and we just get left with 4x cubed. And so we get, we can start to observe pattern here. So when n equals 0, and I skipped over this one, but that's because we don't really need first principles to think about. If you've got the line y equals 1, the gradient of that line is always 0. Okay, so constant, the derivative will always become 0. But I include that here because it follows the same pattern. We can think about it as x to the power of n, because we can think about it as x to the power of 0. Okay. When n equals 1, we get x to the power of 1. Derivative of that is 1. When n equals 2, x squared, derivative of that is 2x. When n equals 3, x cubed, derivative is 3x squared. When n equals 4, derivative of that is 4x cubed. And from this pattern, we might start to conclude that we're observing a pattern that we can continue. And so f of x, if f of x is x to the power of n, then f dash x will be n times x to the power of n minus 1. So we bring the power down to the front and we subtract 1 from the power. We're seeing that happen in all of these. Power down to the front, subtract 1 to the power, gives us 4x cubed, etc. Okay, so we've drawn this conclusion from a really small sample of derivatives, so it's hardly a proof. I'm actually going to be going through the proofs for most of the rules for differentiation. There is absolutely no way that you need to be able to replicate the proofs, but I want you to have an understanding that these rules don't come out of nowhere, okay? So I'm just going to duck back up here because there's some maths that goes on in this proof that is not something you're particularly familiar with, but I just want to emphasize what's happening. So when we expand out, let's say we have x plus a, or let's make it x plus h because it is x plus h, all to the power of n, okay, we observe some patterns, okay, and so let's say, alright, let's start with x plus h all to the power of 0 is going to be 1. I'm going to write this in a particular order for a particular reason, okay. When we have x plus h all to the power of 1, we just get x plus h, okay. When we have x plus h all squared, we get x squared plus 2xh plus h squared, okay. When we have x plus h all cubed, we get x cubed plus 4x squared h. Sorry, my apologies. Sorry, I'm just going to 4x squared h plus 4xh squared. Sorry, I've skipped a rule. I've skipped a line. It's 3x squared h plus 3xh squared plus h cubed. Okay. When we have x plus h to the power of 4, we get x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4x squared, sorry, 4xh cubed plus h to the power of 4. And we can continue this, okay? The pattern that we're seeing is pretty clear with the x's and the h's. So if we have x plus h to the power of 5, we get x to the 5, and then it becomes x4 to the power of h, then it becomes, sorry, I'm going to try and get them lined up. So we get x to the power of 5, this will be some number times x to the 4 times h, plus a number times x cubed times h squared, plus a number times x squared times h cubed, plus a number times x cubed h, sorry, x, sorry, what am I doing? Xh to the power of 4 and plus h to the power of 5. So the question is about these numbers, okay? I'm going to put some ones in there. I'm going to put ones. Okay. And then the question is, well, what goes here, what goes here, what goes here, and what goes here? And then this is going to be 1 again. And what we're actually seeing here, this is a familiar pattern. This is Pascal's triangle. And Pascal's triangle, we get these numbers by adding the two diagonally above numbers in the triangle. So this number 3 comes from 1 plus 2. This is 2 plus 1. Okay. Here we get 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So this next row then, this will be 5. This next row then, this will be 10. Again, this will be 10. And this one will be 5. Okay, and we can continue that pattern on and on and on and on. In terms of each row in Pascal's triangle, we can also use combinatorics to describe the numbers. Okay, so if we think about this 5th row here, this is actually 5 choose 0, this is 5 choose 1, this is 5 choose 2, this is 5 choose 3, this is 5 choose 4, and this is 5 choose 5. Okay. Now, I don't want to get into the maths of combinatorics right now because it's actually not what's important at all, but you're going to see those appear in the proof, and I just wanted to touch on the fact that they are connected to, we call these binomial expansions. When we have x plus h all to the power of n, we can generalize that expansion in that we're essentially going to have n, so if it was x plus h to the n, our first term would be x to the n, our next term would be x to the n minus 1 h. Our next term would be x to the n minus 2 h to the power of 1. Sorry, that was 1, that's h squared. Our next term would be x times n to the power of 3 h cubed, etc. Until at the other end we're going to start to see, we're going to have x cubed h to the power of n minus 3, we're going to have x squared h to the power of n minus 2, we're going to have x h to the power of n minus 1, and we're going to have h to the power of n at the end. And again, these coefficients, in terms of, well, what numbers, it's 1 at the start and it's 1 at the end, what numbers go in here, they are going to be to do with combinations. So this is technically n choose 0, which is 1. This is going to be n choose 1, which is n. Okay. This is going to be n choose 2, which, you know, we could get an ugly algebraic expression for, but we won't. N choose 3, etc. This will be n choose n. So this is n choose n minus 1. This is n choose n minus 2. This is n choose n minus 3. Okay, so I just want to think a bit generally about expanding out that expansion. You're going to see that in this proof here. You do not need to know the theory about that. A bit of that will come back when we talk about binomial distribution later on, but only very slightly. Okay, so essentially, if we generalize this, if we've got x to the power of n, when we expand that out, we get this big ugly expression with all these combinations in here, which we don't really want to worry too much about. Essentially, we've just got x to the power of n, some number times x to the n minus 1 times h, another number times x to the n minus 2 times h squared, etc. So the powers of x decrease, the powers of h increase until we get to the last term where there are no x's at all. Okay, so then if we take our f of x plus h, which is there, minus f of x for our derivative by first principles, we see, like we saw in all those specific examples, the x to the n terms cancel out because we've got x to the n minus x to the n. Then we see every other term has got at least one h in it. So we can factor out that h, which will then cancel down with this. So now instead of there being an h here, there's no h here. Instead of there being h squared here, there's just one h here, okay, etc., etc. And then the next thing, obviously, is that, so the h's are going to cancel out. And now every term except for this first term still has h in it. So when we take the limit as h approaches 0, that'll be 0, that'll be 0, everything in between will be 0, that'll be 0, that'll be 0. And so all we're left with is this one term here, n times x to the power of n minus 1. Okay, as I said, you don't need to replicate the proof. The key is that it is true for any value of n. The interesting thing is, too, that it's not only true when n is a natural number, it would be true for n, any real number. Okay, and so therefore, if n was a fraction, the same rule still applies with a fraction. So multiply by 3 over 2 and subtract 1 from 3 over 2 gives us 3 on 2 minus 1 is a half. And we can obviously write that as 3 root x on 2. Again, multiply by 2 sevenths and subtract 1 from 2 sevenths. 2 sevenths minus 7 sevenths is negative 5 sevenths. Great. Okay. Again, multiply by 4.8, subtract 1 by 4.8, we get 4.8 x to the power of 3.8. So decimals, fractions, pi, okay? And what you're seeing here over in the CAS screenshot is me getting the CAS to actually do that derivative by first principles, okay? So if f of x is x to the power of pi, tell me what the limit as h approaches 0 of f of x plus h minus f of x all over h is, i.e. tell me what the derivative is. And it is pi times x to the power of pi minus 1. So same rule we've seen for any whole number. Similarly, we can have negative numbers. Again, multiply by negative 3, subtract 1 from negative 3, so we get negative 3x to the negative 4, which obviously we could write like this. So we're going to need to be familiar with our index laws, fractional index laws, negative indices, etc., so that we can manipulate these expressions here. Okay. Alright, so we conclude if y is x to the power of n, then dy dx is n x to the n minus 1 for n, any real number. Some other important and useful properties of derivatives, okay? So if we are differentiating a number times a function, okay? So I should probably just say here where k is any real number. So if you have a number times a function, that number isn't affecting how you differentiate, okay? That number can just sit out the front here. You're just getting k times the derivative of f, okay? So what that means is if I have 3x to the power of 7, I'm just doing, and I'm differentiating that, I'm just going to get 3 times the derivative of x to the power of 7, which will be 7x to the 6. Okay, the 3 doesn't actually change the process of differentiation. Yes, I'll multiply it together with the 7 and I'll get 21x to the 6, but the number itself is not actually affecting the derivative. We still just have 3 times the derivative of x to the 7. The other property that we need is that if we are differentiating a sum or difference of two functions, so for example, if we are differentiating x squared plus x cubed, we can simply separately differentiate x squared plus differentiate x cubed. Sorry, so that will become 3x squared. Okay, So you're seeing those two things illustrated in the example down here. So if we are differentiating this whole function, now we wouldn't write out these separate lines, but I want to be clear about the process of what's happening. This 4 isn't affecting the derivative. It can go out the front here, nor is this negative 3. It can go out the front here. So essentially we're finding the derivative of x cubed. We're finding 4 times the derivative of x squared, okay, which is happening there. We're finding negative 3 times the derivative of x, which is happening there, and then the derivative of 2. So we're just calculating the derivative of each of those things separately, and the numbers in front aren't actually impacting how we differentiate. We just multiply them in at the end. But again, we can do that all at once, and I would encourage you to do that all at once. I just want you to be clear about when you can and can't break up a derivative and what you can and can't take out of a derivative. Constant terms, sorry, not constant factors, so if you're multiplying by a number, that can be taken out of the derivative, and if you're adding and subtracting, you can break it up into separate derivatives. Okay, so then this one, for example, essentially we are doing 4 times the derivative of x cubed, which would be 3x squared. We're doing 3 on 2 times the derivative of x squared, which would be 2x, and we're doing 7 times the derivative of x, which is 1, and then the derivative of a constant is 0. So we're going to get 12x squared minus 3x minus 7. And you can absolutely go straight to that final step. Okay, part G, we just need to do some manipulation, sorry, not part G, part B. We just need to do some manipulation before, now I made a big error here that I really want you to be mindful of. These two lines are not equal to each other, okay? I need something new written here. This is the derivative of y with respect to x. It's really important that there's something else written here, because otherwise these two, without writing anything there, you're suggesting those two things are equal, and they're absolutely not equal to each other. Okay, this one here, before we can differentiate, we need to rewrite it slightly so that we can use our rule for differentiating x to the power of n. So I'm not differentiating. This is still equal to g of x, okay? So I don't need to write g dash x. In fact, I can't write g dash x. I'm not differentiating yet. I'm just rewriting each of these terms. 3x to the 4 is fine. I'm going to think about 1 on x as being x to the negative 1. I'm going to think about 3 root x as being 3x to the power of a half. And then I've got my 5. So now that I've rewritten so I can see everything as x to the power of n, and I've only got addition and subtraction, I'm now ready to differentiate. So derivative, and this time I'm not going to write it out separately, so we're going to get 3 times 4, which is 12x cubed. We're going to get negative 1 times negative 1, which is plus x to the negative 2. Be careful with the negative powers. When you subtract 1 from negative 1, you get negative 2. Here we're going to get 3 times a half, so 3 on 2, x, and then half minus 1 is negative half, and then negative 5, when we differentiate a constant, it becomes 0. So you can, if you want, rewrite x to the negative 2 as 1 on x squared again, and you could write x to the negative a half is going to be 1 on root x, okay, but you don't need to, okay. The question asks you to differentiate, and at that point you have differentiated. Okay, so in many ways, I would encourage you to not go further than you need to. The issue is if you were then going to substitute a number into this derivative, for example, it might be helpful to get it into this second form so that you can actually see what x to the negative 2 means, what x to the negative half means. The next point I want to make is that whilst we can break up a derivative if there's addition and subtraction, okay, so we know that the derivative of f of x plus or minus g of x is just the derivative of f of x plus or minus the derivative of g of x. That is not possible if it is multiplication, okay, so that's what we're seeing here, or division inside the derivative, okay. The derivative of the product of two functions is not simply the product of the derivatives of those two functions. Similarly, the derivative of a quotient of two functions is not simply the quotient of the derivatives of those functions, whereas the derivative of a sum of two functions is the sum of the derivatives of those two separate functions. Okay, this is really important. Down the track, we're going to look at product rules and quotient rules that will enable us to differentiate these products and quotients. However, it's quite possible that we might be given functions and expressions that involve products and quotients, but we don't actually need the product rule and the quotient rule because we can simplify, expand, tidy it up, rewrite it in a different way using some algebra so that we can get it into a form that we can actually differentiate without needing the product or the quotient rule. And I would say to you that even when we do introduce the product and the quotient rules in a couple of lessons' time, I would still, if I can simplify the expression first to avoid having to use the product or quotient rule, I absolutely will. Okay, so in this example here, for example, part A of example 2, we have a product of two things. This is something multiplied by something else. Okay, and so we cannot just start differentiating things as they are. We need to first of all expand this out. We could use the product rule, but actually in the long run it's a nicer derivative if you expand it out and tidy it up first so that you don't need to use the product or the quotient rule. Okay, so we're going to expand these brackets. We've got a bit going on here. I might also, before I do that, just write this as, so it's still equal to x. We haven't differentiated. I'm just going to write this as t to the power of a half. And this is already t to the negative 4, so that's fine. Okay, so let's expand out the bracket. So again, we're not differentiating yet. It still equals x. Doesn't equal dx dt. So 1 times t to the half is t to the half. Plus 1 times t to the negative 4 is t to the negative 4. Plus t times t to the half. So it's t to the 1 times t to the half. We add powers. That's t to the 3 on 2. Sorry, it's not plus, it's minus, because it's negative in the first bracket. And then negative t times t to the negative 4, again it's going to be negative. Again we add powers because we're multiplying. T to the 1 times t to the negative 4 is t to the negative 3. Okay, so now we have it in a form that we can differentiate. Derivative of x in terms of t is dx dt. And so we're going to get half t and then subtract 1 from half, which is negative half. This will become minus 4 times t to the negative 5. This will become plus 3 on 2 t to the 1 on 2. 3 on 2 take away 1 is 1 half. And then we're going to have minus 3t to the minus 4. Again, you can, if you want, rewrite this. This will be 1 over 2 root t. This will be minus 4 on t to the power of 5. This one will be 3 root t on 2. And this one will be 3 on t to the 4, okay? But you don't need to. You're perfectly fine here. You have done what the question asked, which was to differentiate. The second line isn't any more simple. It's just a different way of writing the same things. So there isn't an issue of simplification here. It is just a different way of writing it. All right, part B here. Again, it's technically a product of two things because it is 3x minus 2 on root x times 3x minus 2 on root x. So we could potentially use the product rule. There's actually another rule we'll revisit in the next video, which is the chain rule. Could be used here as well. But again, when it's only a power of 2, I would probably expand out and then differentiate rather than use the chain rule. Okay. So we don't technically need to write that out because I know how to expand a perfect square. Well, it's minus in this instance. A minus b all squared is a squared minus 2ab plus b squared. So let's do the same here. So we're going to have 3x squared minus 2 times 3x times 2 on root x, and then plus 2 on root x all squared, expanding out our perfect square. So again, it's not h dash x here. We haven't differentiated yet. We're still just expanding out and tidying up the expression into a form that we can then differentiate. Okay, so this is 9x squared. Now I'm going to write that as x to the half. Alright, so in this case we're going to have, technically here we've got 2 times 3 times 2, so that is going to be 12. And then we've got x to the 1 times x to the negative half, or x to the 1 divided by x to the half, so we subtract powers, so x to the power of a half. And then we're going to have 4 on x when we square that. Alright, so now we can differentiate. H dash x is going to be 18x minus 6x to the negative half. And then actually I might write this 4 on x as 4x to the negative 1. So that's going to be minus 4x to the negative 2. Perfectly done and finished at that point. If you want to, 18x minus 6 on root x minus 4 on x squared. They're the same thing and both perfectly correct answers to the question. Okay, final example here. We've got a quotient, one function divided by another function. So we cannot just differentiate the numerator and differentiate the denominator. We have to rewrite it so there isn't a division of two functions. Division of a number in a function is fine, okay? Because the derivative of the number is 0, so essentially you don't need a different rule. But derivative of two functions, so even if we had x squared on x, you'd have to actually write that as x before you differentiated it. Okay. Alright, so we want to simplify this, so we're going to need to do a bit of work here before we can differentiate. So this is 3x plus 2 over 2x to the half, which is the same as doing 3x over 2x to the half plus 2 over 2x to the half. Okay, so that's 3 on 2, and we subtract powers, so it's 1 minus a half, so that's x to the half. This is essentially x to the 0 up here, so again we can think about subtracting powers. 2 divided by 2 is 1, so we don't need to write that. We're going to have x to the negative half there. Okay, so now that it's in a format that we can differentiate, y is equal to that. So when we have y in terms of x, the derivative is called dy dx. So we're going to get half times 3 on 2, which is 3 on 4, x, and then we subtract 1 from 1 half, which is negative a half. This will become minus 1 half, x, and then we subtract 1 from negative a half, so we get negative 3 on 2. So again, different ways that you could choose to write that, but it's perfectly fine at this point. We have done what the question asked, which was to differentiate the function. In terms of differentiating using your CAS, I actually haven't got my CAS arts here. Actually, I could just pop it on the top here. So in terms of calculating a derivative with your CAS, there are a number of ways to access the derivative menu, for the calculus menu, and then derivative, number 1. Or the quicker way, given that we actually differentiate a lot, there's a keyboard shortcut, Shift minus. So Shift is above the 7, Shift minus will bring up the derivative template. You simply enter then, I want to differentiate with respect to x. Oops, sorry, apologies. I want to differentiate with respect to x, and then put whatever your function you want to differentiate is. And it will calculate your derivative for you. So Shift minus is a really key one. You can also get the derivative from the template palette. It is there, but of all of them I would always be doing Shift minus. Okay. Derivative at a point can also be used, so just quickly let me bring that back up. So if you noticed in the calculus menu for number 2 was derivative at a point, and so you tell it what's the variable in your expression, what value do you want to calculate the derivative at, and it will bring up a special template for you. But again, I would rarely use that because I would just use my derivative. So I would do Shift minus, and then if I wanted to calculate a derivative at a point, I would put, given that x equals 2 myself. Okay, but up to you. Alright, so that's just some instructions about how to use your CAS. Right now though, I want you to be practicing differentiating by hand. We'll get into using the CAS more when we do some applications, but just becoming aware of the different ways you can access derivative using your CAS. So there's a worksheet to do today, and it's found in the back of your blue booklet in Appendix B.